Today we're tackling one of the biggest questions in motor control: how to choose the right starting method. We'll explore the DOL, direct online, starter, star connection, delta connection, and the star-delta connection. I know many engineers and technicians try endless searches online, trying to find practical solutions for real-world applications. Well, look no further. In this video, I'm breaking down each method step by step, showing you exactly how they work, when to use them, and a few surprising tips to help you avoid common mistakes. By the end, you'll have the confidence to pick the right approach for any motor setup. So if you're ready to master motor starting methods and save time on the job, stick around. Don't forget to like and subscribe as token of appreciation. Let's get started. Let's start by discussing the direct online, or DOL starter. This is one of the simplest methods for starting three-phase induction motors. When you use a DOL starter, the motor is directly connected to the power supply without any additional control devices. This means that when the starter is activated, the motor receives the full line voltage immediately. As a result, the motor develops maximum torque right from the start. This is particularly advantageous for applications that require high starting torque, such as pumps, compressors, and fans. However, there are some important things to consider. The DOL method leads to a high inrush current, which can be several times the motor's rated current. This sudden surge of current can create voltage dips in the electrical system, potentially affecting other equipment connected to the same supply. This is especially critical in facilities with multiple motors starting at the same time, as it can cause circuit breakers to trip or lights to flicker. To summarize, the DOL starter is straightforward and effective for smaller motors and applications where high starting torque is needed. However, due to the high starting current, it is essential to assess whether your electrical system can handle this load. Let's discuss the delta connection. This configuration is another common method used in three-phase systems and is often employed for motor operation once the motor has reached a certain speed. In a delta connection, the ends of the three windings are connected together to form a closed loop, creating a triangular shape. Each winding connects to the line voltage directly, allowing the motor to operate at full voltage. For example, if the line voltage is 400 volts, each winding in a delta connection also receives 400 volts. One of the main advantages of the delta connection is that it provides higher torque and power output. This makes it ideal for applications that require high starting torque and where the load demands significant energy, such as conveyors, crushers, and large pumps. Unlike the star connection, the delta configuration does not provide a neutral point. This means that it is typically used for systems that do not require single-phase power or where a neutral connection is unnecessary. Another important aspect of the delta connection is that it allows the motor to run efficiently at its rated speed and torque. This is because the motor receives the full line voltage, which maximizes its performance capabilities. I also want to show my students that how easily you can make the electrical control circuit and PLC control circuit. See, in an electrical control circuit for direct online, or DOL, the motor is directly connected to the supply voltage, allowing it to start immediately at full voltage. The circuit consists of a start push button, stop push button, a contactor, and an overload relay. When the start button is pressed, the coil of the K1 contactor is energized, closing its normally open contacts. This allows the current to flow to the motor, starting it. The overload relay is connected in series with the motor to protect it from excessive current. If the motor draws too much current, the overload relay will trip, breaking the circuit and stopping the motor. When the stop button is pressed, it de-energizes the K1 contactor coil, opening the contacts and cutting the power to the motor. This simple and efficient control method is widely used in small motors. I also want to make ease for my students. In a PLC-controlled DOL circuit, the same motor and components are used, but the control logic is programmed into the PLC. Do not be scared of it. The start and stop buttons are connected to the PLC's input terminals. The PLC program is written to interpret these inputs and control the output to the contactor coil. When the start button is pressed, the PLC sends a signal to energize the K1 contactor coil, starting the motor. The overload relay still functions to protect the motor, and the PLC continuously monitors the motor's status. If an overload condition is detected, the PLC can trigger a fault alarm or stop the motor by de-energizing the contactor coil. This method offers more flexibility and control, as the PLC can also integrate with other systems for data logging, fault diagnosis, or remote monitoring. I have connected overload in main supply circuit to ease you for understanding. However, you can also input this, just like the start push button and stop push button to PLC, and make the program accordingly. In existing arrangement, this PLC will work to start and stop the motor from PLC. Now let's discussing the star connection, also known as the Y connection. This configuration is commonly used in three-phase systems and is crucial for motor starting methods like star-delta starters. In a star connection, the three phases of the motor windings are connected to a common point, which is referred to as the neutral point. The other ends of the windings are connected to the power supply. This setup allows each winding to receive only a fraction of the line voltage. For example, if the line voltage is 400 volts, each winding in a star connection would receive about 230 volts. To avoid any confusion, let me clarify. Line-to-line voltage, also known as phase-to-phase voltage, which is 400 volts, though this can vary depending on your country's electrical standards. Similarly, line-to-neutral voltage, often called phase voltage, which is 230 volts, but keep in mind that this can also differ by country. One of the main benefits of the star connection is that it reduces the starting current when the motor is first activated. Since the voltage across each winding is lower, the inrush current is also limited, which helps to prevent damage to the motor and reduces the mechanical stress on connected equipment. The star connection is particularly useful in applications where high starting torque is not required. It is ideal for running motors at reduced speeds or in situations where gradual acceleration is beneficial, such as fans and pumps. Additionally, the star connection allows for the possibility of using a neutral wire. This is important in some applications where a single-phase supply is needed, as the neutral point can be accessed for this purpose. In summary, the star connection is essential for reducing voltage and current during startup, making it a great choice for specific applications. After gaining clarity on the star and delta connections, let's move on to the star-delta connection in the same motor together. The star-delta starter method combines both the star and delta configurations, allowing us to make the most of each. The star-delta starter is widely used in the industry to reduce the inrush current of large motors during startup, which helps protect both the motor and the electrical system. Here's how it works. Initially, the motor starts in a star configuration. This setup reduces the voltage across each winding and therefore limits the starting current, making the start smoother and safer for the motor. After a brief period, usually just a few seconds, the connection automatically switches to delta configuration. Once it's in delta, the motor runs at full line voltage, giving it the full power needed to operate efficiently at its rated speed. To change from star to delta configuration, we use magnetic contactors for the switch from star to delta. I'll also explain its method of operation later. The star-delta connection is especially useful for larger motors, where a high starting current can lead to electrical stress or even mechanical strain. By using this technique, we get a smooth startup while reducing wear on the motor, and then shift to full power when the motor reaches speed. This simple switching method not only improves performance, but also helps extend the motor's lifespan by minimizing startup stress. With this setup, you get the best of both worlds: a controlled, low-current start with the star connection and maximum operating power with the delta configuration. Now, let's move to the electrical control circuit for the star-delta operation. In this setup, we primarily use three contactors labeled as K1, K2, and K3, each playing a key role in controlling the motor's transition from star to delta. Here's how it works. This is a very important step. When the motor starts, the K1 contactor is activated, which connects the motor windings in a star configuration. At the same time, K3 is also engaged to ensure the motor is in the star mode, which keeps the starting current low and reduces stress on the motor. This configuration is maintained for a short period, typically set by a timer in the control circuit. After the timer completes its countdown, K3 automatically disengages, and the K2 contactor is then activated. This action switches the winding configuration from star to delta, allowing the motor to receive full line voltage. With the motor now in delta mode, it can operate at full speed with maximum efficiency, delivering the power required for its load. This changeover is smooth and carefully timed. By starting in star mode, we limit the current at startup and then seamlessly shift to delta mode to achieve full operating power. This approach not only ensures a controlled start, but also minimizes mechanical and electrical stress on the motor. With K1, K2, and K3 working in sequence, the star-delta starter provides an efficient, reliable method for operating larger motors, making it a popular choice in various industrial applications. The very important thing that I consider to share is understanding PLC control along with the electrical control, because the world is moving towards advancement to control motors from PLC, DCS, and SCADA. To have 100% clarity, I always share this as a bonus with you, something that will take your understanding of PLC control circuits to the next level. Whether you're a student, engineer, or technician, learning how to work with PLCs is a game changer. It's not just about the theory, it's about how to use that knowledge to make real-world systems work efficiently and safely. I know that getting hands-on with these control circuits can be challenging, but don't worry. This video is designed to give you the practical experience you need with easy-to-understand explanations. You'll see how PLCs make complex systems easier to manage and how you can troubleshoot and optimize these systems to keep everything running smoothly. All right, let's move to the PLC setup. To keep things simple and clear, I've set up the overload relay in the PLC just like the traditional electrical control circuit, instead of making the overload an input to the PLC. My goal is to help you avoid any confusion by showing you a familiar setup. In electrical control, we're used to working with relays like K1, K2, and K3 to manage switching from star connection to delta connection. Well, in the PLC setup, we're doing something similar. Here, the PLC output handles the K1, K2, and K3 relays, just like in electrical control. The big difference? Instead of wiring start and stop buttons directly into the relays, we're connecting them to the PLC as inputs. Also, we are not using a timer with the PLC as we used in electrical control, because the timer will be added in the PLC programming for controlling the switching. I have made another video for simple timer programming to understand timers in PLC. Okay, now start and stop buttons are digital signals going into the PLC, which then decides when to activate each relay based on the logic we've programmed. It's a similar approach, but gives us way more flexibility for controlling and monitoring the system. By setting up the PLC this way, you'll get a clear view of how the system functions. Just like with electrical relays, it will have the same function to trigger K1 contactor and K3 contactor together for a few seconds to have star connection and avoid high inrush current during motor startup. After that, K3 is switched off, K2 is energized, and K1 remains on, allowing the motor to receive full line voltage. With the motor now in delta mode, it can operate at full speed with maximum efficiency, delivering the power required for its load. If you're interested in learning more about programming the star-delta connection or want a step-by-step tutorial on how to set it up, just let me know in the comments. I'd be happy to make a detailed video to guide you through each part of the process. I've included a simple and clear comparison of the DOL, star, delta, and star-delta connections to help you understand each method's benefits and uses. By breaking it down into easy-to-follow steps, I aim to help you choose the right starting method based on your specific motor control needs. Whether you're just starting out or need a refresher, this comparison is designed to make it straightforward and accessible.